In this video, I'm going to go through the Edexcel A-level Chemistry paper from 2020. And this is paper 1, Inorganic and Physical Chemistry. I'll just do the first half of the paper in this video and finish it in a later one. Okay, so the first question. Which equation shows the third ionization energy of aluminium? So that's removing the third electron. So that's when you're going to get Al2 plus going to Al3 plus. And of course, everything should be in a gaseous state. So our answer is B. Okay, more on ionization energies. Which element in this table is in group 2? Right, so it gives the first, second, and third, okay, and so on, ionization energies. What we're looking for is we're looking for a gap, because if you've got, like, say, for example, magnesium, which would be electronic structure 282, the first one would make it to 281, and the second to 28, and the third one to 27. Okay, so that means you would get this third ionization energy would be much bigger than the other two because you're removing it from the second quantum shell rather than the third shell. So we're looking for a jump after 2. Okay, so I would say the first one, look at W, they're going up fairly steadily, so I don't think it's that. X, again, they're all going for, there's no big jumps there. Y, 590, and there is a big jump here, goes up by a factor of 4. Okay, so I think it's got to be Y is the answer. And just to check, it's not Z. Well, Z is probably actually in group 1, isn't it? Because you can see there's a big jump here between the first and the second. So Y would be the answer there. So that's our answer, C. Okay. Now, we have got the first ionization energy of 8 successive elements from the first 20 elements of the periodic table. And which one represents the ionization of oxygen? Well, you can see here that when you go from E to F, okay, that is you're starting a new quantum shell. So I would imagine that that is when you're going from neon. So E would be neon, and then sodium would be F. There you go. So neon is coming from the second quantum shell, sodium from the third. And so if we count back, neon, E, that's D, C would be oxygen. And of course, you're getting that little drop there because when B is nitrogen. So there's you're removing the electron from 2p. When you're removing it from oxygen, you're still removing it 2p, but you have a slightly lower ionization energy because in oxygen, that electron is paired. The one that you're removing is paired up, so you get repulsion. So C is the answer there. Okay, I'll leave that periodic table there because it says give the formula of a stable ion that is isoelectronic with a magnesium ion. So isoelectronic means it's got the same electronic structure. So we mean, right, it's magnesium is 282. So the magnesium ion is 28. So we want another ion which has got that is also 28. Well, you could have sodium. Yeah, sodium is 281. That's kind of the sodium ion. You could have that one. Okay, you could also have fluorine. That is 27. And so that gains 1 to form the F minus ion. So you could have F minus, or you could have oxygen. That would have to gain 2. That'd be O2 minus, or you could have N minus, N3 minus, yeah, that's losing 3 electrons, or you could have aluminium, which would be, because that's aluminium is 283. So yeah, you could have any of those. You only have to give one though, of course. Okay, so here is about a 4-mark question. 4 marks for this one. Students say that the elements scandium and zinc are D-block elements, but are not transition metals. Discuss this statement using appropriate electronic configurations to support your answer. Okay, right. So scandium. Let's talk about scandium. Well, let's see what's the definition of a D-block element. Is just a one. The last shell to be filled is the D shell. Last filled subshell is D. But the definition of a transition metal is a bit different to that. A definition of most people use for transition metals would be transition metal is one that forms a stable ion, or an ion, forms an ion with a partly filled D shell. Okay, so that's the definition of transition metal. Now we see that scandium and zinc aren't actually transition metals who use that definition. Scandium is going to have the electronic configuration. Well, you can see it's here. So 4s is filled. I've got 1 electron in 3d. So it's 3d1, 4s, 2. Now scandium only forms the scandium 3+ ion. And so the scandium 3+ ion would be, well, we'd have an argon core, and it would have no electrons in the D shell. Okay, so it hasn't got a partly filled D shell, it's got an empty D shell, and that's the only ion that scandium forms, so it's not a transition metal. Now let's look at zinc. Well, you can see that zinc is, if you count along here, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so the electronic structure of zinc is Zn 3d10 4s2. Right, zinc only forms the Zn2+ ion. Okay, and that would have the electron, doesn't form any other ions, and that would have the electronic structure 3d10. And of course, that's not a partly filled D shell, that's a full D shell. So that wouldn't count as a transition metal either. So that's all you need for your 4 marks there, I think. Right. Right, about acids and bases. What's the order of decreasing pH? So what we're looking for is we want the acids in order of increasing strength, and don't we? They've all got the same concentration. So the strongest one would dissociate the most, so it would give the lowest pH. So we're looking for increasing strength. Right, so we've got HCl, which is obviously the strongest acid here. So that would give the lowest pH. And then we have got ethanoic acid. Okay, which is a weak acid. And we've also got chloroethanoic acid. This is chloroethanoic acid here. Well, chloroethanoic acid, we've got a chlorine there, is a slightly stronger, or quite a lot stronger acid than ethanoic acid, because this chlorine is electron withdrawing. It's going to be delta minus, it's going to be delta positive on that carbon. So that means when it loses the proton, and it's got a negative charge on there, this chlorine here it drags some of the, it decrease the intensity of the negative charge. And so it makes it a slightly stronger acid. And if you had dichloroethanoic acid, it'd be even stronger, and trichloro would be even stronger still. And so what we were looking for then, the weakest acid of that lot is going to be ethanoic. The next one is a bit stronger, is chloroethanoic, and then the strongest one is HCl. So the answer is A. Okay. Right. Right, B, a solution of methanoic acid has a concentration of 0.24 mole per decimeter cubed and a pH of 2.2. And we've got to calculate the the pKa of the methanoic acid. So we're going to calculate the Ka. So I'm just going to write down what happens there. So you get Ha is going to dissociate into A minus and H plus. And we write, we write down the expression for Ka. Ka is equal to, of course, A minus H plus conc divided by the concentration of the undissociated acid. So let's say we have got the start concentration here. When I mean start, I mean, so this is, we just put the methanoic acid into water, and before any of it has a chance to dissociate, so the concentration of that is going to be 0.24. And the concentration of A minus, of course, will be 0 because none is dissociated. And the concentration of H plus, well, it's not really going to be 0, but we can, because there's always some H plus in neutral water, but we can ignore that. It's insignificant compared to the amount that's going to be released from the acid. So we'll call that 0 as well. And then here's the equilibrium concentration when it has reached equilibrium. Right, let's say that HA, the concentration has dropped by an amount X. So that means, well, the concentration of A minus at equilibrium will be X, and the concentration of H plus will be X as well, because when one of those dissociates, it gives you one of them and one of them. Okay. Now we know what X is, because X is a hydrogen ion concentration, and they tell us the pH. Okay, so hydrogen ion concentration, which is equal to X. Well, that is going to be 10 to the power of minus 2.2. That's the pH, which is equal to 6.31 times 10 to the minus 3. Right, now we're going to put the numbers into this equation here, okay, to find out Ka. So, right, so I'm going to put in, right, so Ka is going to be equal to the concentration of A minus. Well, the concentration of A minus is equal to the same as the hydrogen ion concentration, it's that. So that's going to be 6.31 times 10 to the minus 3. The hydrogen ion concentration is the same, so that's that squared. Now the concentration of HA is 0.24 minus X, so that's going to be 0.24 minus 6.31 times 10 to the minus 3. Okay, evaluate that in your calculator and you get 1.703 times 10 to the minus 4, and the units would be mole per decimeter cubed. That's the value of Ka. And if we remember what the definition of pKa is, pKa is equal to the minus log of the Ka. So it's minus log of 1.703 times 10 to the minus 4. And that gives us 3.77. That's our answer. Right, here's a question about buffers now, okay? Now, which of these would form a buffer solution, and a little bit more information, with a pH below 7? Now, what do we need for a buffer? A buffer is made up of a weak acid and its conjugate base. So, in other words, HA and some A minus. Right, so we can see A doesn't have, it's a strong acid and a strong alkali, so that's not it, obviously. Right. Right. C is completely wrong because that's a strong acid and an alkali. Now, so it's got to be B or D. Right. Now, let's see what would happen if in B. So if we had, we've got excess of that, and we've got NaOH, we'll call that OH minus. Right. That is going to react to give you the its weak base, its conjugate base. Okay, now because we've got excess of this, that means, so like we have like more moles of that than that one. So say we had like 4 moles of that and only 3 moles of that, and 0 of that to start off with. At the end, you would have 1 mole of that and you'd have 3 moles of that. So you would have a mixture of the strong acid, weak acid, sorry, and its conjugate base. So B is the answer. Just to show you, D is wrong. Well, what would happen if you did D, and the pH would be less than 7? If you had D, well, you'd end up saying if you had an excess of NaOH, let's say we had 3 moles of that and 5 moles of OH minus, none of that to start off with. Well, at the end, you'd have 0 of that, and you'd still have some, of that, but you'd still have some OH minus. You wouldn't have any of the weak acid, so it wouldn't be it wouldn't be a buffer solution. Okay. Okay, bromothymol blue, methyl orange, and phenolphthalein are indicators. Okay, which of any of these indicators could be used in the titration of ammonia and ethanoic acid? Well, you couldn't do a titration with an indicator there, because if you look at the right here is a titration curve. This is a strong acid, strong base. It would be like that. Okay, that's a strong acid, strong base. A weak acid, strong base, you get something like that. Okay. A strong acid and a weak base, you would get something like that. So if you got a weak acid and a weak base, you just get a very indistinct endpoint there, which you wouldn't be able to detect with an indicator. And so you can't do a titration really of a weak acid and a weak base. So our answer is D. You should also, what's flagged up there really, you may be expected to know that, I suppose, that phenolphthalein is okay as long as you've got a strong base. Yeah, it won't work with weak bases. And you probably also know that methyl orange is okay with a strong acid but not a weak acid. But bromothymol blue is a bit of an obscure indicator, and I don't think anyone really would expect you to know, where or what pH range that changes color. So that should sort of flag up that maybe it's a bit of a trick question, and it's none of them is the answer. Okay, this is about transition metals and transition metal complexes. Describe the bonding in the element chromium and use your answer to justify why it has such a high melting temperature. Okay, so this is really, it's 4 marks, but it's barely above GCSE. It's just, we're talking about metallic bonding here, aren't we? So what is a metal? We have a actually, I'll draw a bit differently to that. We have positive ions. Okay, they've lost their valence electrons, so they're going to be positive ions. You've got a regular arrangement of them. Okay, I could draw another layer, but I won't bother. And in between them, you've got these green things. These are delocalized electrons. Okay, so I would say something like a regular arrangement of positive ions in a sea of delocalized electrons. Okay, and why has it got a high melting temperature? I think you need to say there is a strong attraction, say electrostatic attraction, between the positive ions and the negative electrons. Okay. All right. Chromium 3 sulfate dissolves in water, a green solution containing the hex aqua ion here. What is the shape? Well, whenever you've got 6 ligands like that, it's always, of course, octahedral. Okay, and a bit of a longer question. I explain why chromium complex ion is colored. Right, there's only 3 marks going for that, and I'm probably going to give too much information here. I'll give about 5 points, but this is what occasionally you do get more than 3 marks given for that. So I'll say, right, why does it look colored? I'll say, first of all, white light is a mixture of all the frequencies. Right, the complex, the chromium ion only absorbs certain frequencies, colors. Okay, so it looks the color of those frequencies it doesn't absorb. Right, why is it absorbing visible light? Okay, it's because absorbs light, the energy promotes electrons from one d orbital to another. You may say, well, how does that work? Because all the d orbitals have got the same energy. Well, they have, but when the ligands bind, you find that the d orbitals have different energies. We say that they lose degeneracy. That means they just have 2 of them actually become higher in energy and 3 become lower in energy. Okay, so you can promote electrons from one d orbital to another. Okay, that's more than enough for the 3 marks there. Okay, right. Now this is about EDTA, which is a hexadentate ligand, multidentate ligand. Right. Now, it says the equilibrium constant for this reaction is this, okay? Right. And that means that that reaction is extremely far over to the right. The position of equilibrium is very much that way. There's hardly any of the on the left-hand side. Also, we can say, how does that relate to delta G? Well, we know that delta G is equal to minus R gas constant T ln K. Right, now because K is very big, it's enormous, and because it's minus that, that makes delta G in the forward direction very negative. So that means it clearly is feasible. Delta G is very negative. Well, why is delta G so negative? Well, let's have a look at the expression for delta G. Well, delta G is equal to delta H minus T delta S. Okay, and we've got to explain why delta G in the forward reaction is so big. Okay, well, delta H, now it says here, changes in entropy. Well, delta H, that's equal to approximately 0 for this reaction. You may not really need to mention that, but it's about 0 because you're going to be breaking 6 dated bonds and then forming 6 new dated bonds there. That's about 0. Now we can see that delta S for this reaction is going to be positive and large. Why is it going to be positive and large? Well, because the disorder increases as you go from left to right. And how can we see that? Well, we can see that is the case because on this side of the equation, the reactant side, we've got 2 aqueous species. We've got the chromium complex, and we've got EDTA. But when it goes forward on the right-hand side, you can see you've got, well, the complex, and you've got 6 water molecules. So you've got 7 aqueous species there. So the amount of disorder has gone up considerably. So delta S is large and positive. So that is going to make this, because T can only have a positive value, of course, the absolute temperature. So that's going to make that negative. And that in turn is going to make delta G very negative. Which of course essentially means that reaction, it's negative in the forward direction, it's positive in the backward reaction. It can't really go backwards. It wouldn't be thermodynamically feasible. Okay, so that should get you the marks there. Right, carrying on with transition metals. We've got vanadium to chloride. Okay. And you can oxidize it. So we've got vanadium is in the 2+ oxidation, the 2+ ion, obviously. It can be oxidized by bubbling gaseous chlorine through the solution in the absence of air. And of course, vanadium can have oxidation states of it can have +2, it can be +3, and it can be oxidation number +4 with a species like that. And also oxidation number +5, like that, the dioxyvanadium ion. Okay, so it can have variable oxidation number. And if you oxidize it with the chlorine, well, does it oxidize it just to the 3+, or the 4+4, or the +5 oxidation state? We've got to find that out. Okay, so what we're going to do is we need to find out the moles of V2+. Okay, so let's do that. The moles of V2+, well, we can work out that. That's concentration times the volume. So the concentration is 0.1, and the volume is 0.04. That's going to be 4 times 10 to the -3 moles of that. Okay, and now we have to work out the moles of chlorine. We need to see the ratio that they react with each other in. Now the moles of chlorine, we're going to work that out because it gives us the molar volume. Okay, and it tells us how much chlorine, 144 centimeters. So that's equal to volume over the molar volume. Well, 140 centimeters, we'll convert that to dm cubed. That's 0.144 dm cubed. Divided by 24. Okay, that gives us 6 times 10 to the -3 moles. Okay, so we have a look at this equation here now. I'm going to say, look, 1 mole of chlorine uses up 2 moles of electrons. Okay. So that means 6 times 10 to the -3 moles uses up 2 times 6 times 10 to the -3 is equal to 0.012 moles of electrons. Okay. Right, where are those electrons coming from? They're coming from the vanadium. So the moles of so we say that each mole of vanadium is giving away 0.012 divided by the number of moles of vanadium, which is 0.004. We worked that out here, yeah. Okay, so that means each mole is giving away, that's equal to 3 moles of electrons. Okay, so that means that well, it's giving away 3 moles of electrons. So if the V2+ is oxidized to V3, that's 1 electron, isn't it? If it goes to the, so that's a +3 oxidation state. If it goes to the +4 oxidation state, that's 2 electrons. If it's going to the +5 oxidation state, it's 3 electrons. So we can say that the vanadium is oxidized up to the +5 oxidation state. That is our answer. Okay, the chlorine will oxidize it up to that. Right, the next question, it says, right, state the initial and final colors you would see as the chlorine bubbles through the aqueous vanadium 2 chloride. So it's going to go from V2+ up to the +5 oxidation state. And as I say, the formula of that is, the most common ion for that is dioxide vanadium, VO2 plus. Okay, what colors are those things? Well, this one is violet, and this one is yellow. So the initial color is violet, and by the time the chlorine is completely reacted with it, it should have turned yellow. Okay, this is just straightforward recall, really. Question is about dissolving different compounds. Which of these compounds is the most soluble in water? So you've got group 2 compounds there. I've done group 2 over here. I'll get rid of beryllium because we don't really worry about that. But you should know that as you go down group 2, the sulfates become less soluble. And as you go up group 2, the hydroxides become less soluble. So, well, it's not asking about hydroxide, so that's irrelevant. So barium is one, isn't it? The most soluble. That's the least soluble. It's magnesium is the most soluble. Let's say that is just a matter of recalling that there. Okay, what is the value in kilojoules per mole for the standard enthalpy of solution of magnesium chloride then? Okay, so all right, so let's look at this Hess's law cycle, this energy cycle. Well, let's look at this red arrow here. What are we doing there? We are forming 1 mole of ionic compound from its gaseous ions. So that is the lattice enthalpy there, the red one. And that is minus 2526. Okay. And then on this one, we've got gaseous ions dissolving into water, right? So that's going to be the hydration of the magnesium ion, which is minus 1912.21, sorry. And 2 times the hydration, because we've got 2 moles of chlorine there, so that's minus 381. So we add that lot up together, we get minus 2683 kilojoules. Now, it's asking us for the enthalpy change of solution. Where is the enthalpy change of solution? Well, it's that there, isn't it? When you get a solid and you turn it into the ions dissolved in water, that yellow arrow. So to the yellow arrow, what are we doing? Well, we are going against the red arrow. So I'm going to flip that sign. So delta H sol is going to be equal to, I'm going against that. So I've got to flip that to make it a positive. So plus 2526. And we're going with the green arrow. So keep that. So that's minus 2683. So we can see that is minus 157 is the answer there. So B, that is our answer. Okay, solubility of 2 compounds in different solvents was investigated, and a summary of the findings is shown. Okay, explain the finding of these by considering the interactions between the compounds and each of the solvents. Okay, so right, let's do the why the potassium bromide is soluble in water. Okay, so KBr is an ionic compound, obviously, K plus ions and Br minus ions. So if you want to dissolve it, you need to break the strong electrostatic attractions between the ions. And obviously that's going to be very endothermic. Right. So how can that happen? Well, it's because at the same time you're having an exothermic process occurring. And what that is, the exothermic process is that the H2O molecules are polar and they're going to form interactions with the charged ions. So for example, with the potassium ion, which is positively charged, the water molecules, well, there's going to be strong electrostatic attraction between the because the water molecules has a partial negative charge on the oxygen. So you're going to form this exothermic process is the attraction of the water molecules to the K+ ions in that way, and the Br- ions, well, they're going to go the other way around. It's going to be the hydrogen, which has got a partial positive charge. Okay, like that. Right, that's going to be attracted to the bromide ions. Okay, so the energy that you release in this process, okay, is approximately equal to the energy that you've got to put in for this process here. And so that means that it will dissolve. Now, if you try to dissolve it in hexane, hexane is not polar. So you're not going to, you just have to have that endothermic process, yeah? And you wouldn't get any, you get the endothermic, you'd have to put loads of energy to break up the lattice, but you wouldn't have, get energy out because the hexane molecules are not polar and they're not going to be attracted to the positive potassium ions and the negative bromide ions. Right, now let's talk about methylpentane now. So methylpentane is soluble in hexane, but it's not soluble in water. Okay, so methylpentane, like that. Okay, so all it is you've only got carbons and hydrogens there. Okay. Right, that's all you've got there. You've only got carbons and hydrogens. They're approximately the same electronegativity, so there's no dipole in that molecule. There's no dipole. So that means the only kind of intermolecular forces you're going to get are London forces. Okay, so that means it's not good. Methylpentane is not going to be able to interact with water because water is polar and it forms mostly hydrogen bonds. If the methylpentane did mix with the water, it would break the hydrogen bonds and get in between water molecules, break the hydrogen bonds, and that would be unfavorable. So it's not going to, it won't mix with it. Of course, hexane is extremely similar to that. Hexane is just made up of carbons and hydrogens again, and so there's no dipole in that. So you are just going to get London forces in pure hexane, the only intermolecular force, and pentane can form those as well, so they can interact with each other. Okay, this question about the hydrated magnesium nitrate. The group 2 nitrates decompose when heated. State 2 observations, see when it's heated. Well, let's think of the equation first of all. So you're going to get MgNO3 twice solid, right? Oh, sorry, and you've got, it's hydrated. So you've got water molecules there. So when you heat it up, you're going to get water molecules coming off, of course, XH2O, and that will decompose to magnesium oxide, nitrogen dioxide, and oxygen. And they're both gases. So what would you see? Well, this gas is green. This gas is brown. Okay, nitrogen dioxide is a brown gas. So you see a brown gas being given off from the white solid, which is, this would be white, of course. And what's the second one you see? I think you probably see condensation at the top of the test tube from the water crystallization. At the top of the tube, or you might see some sort of steam coming off as well. Right, explain the trend in thermal stability of the group 2 nitrates. Okay, so, right, they become, as you go down the group, magnesium, calcium, strontium, barium, they become more stable. So the magnesium is the least stable, and the reason for that is due to the size of the ions. Right, magnesium ions are the smallest ones. Barium, of course, is still 2+, but quite a lot bigger. So this has got a higher charge density. That means it's better, it's more able to polarize the nitrate ion. And the polarization of that ion, that will weaken the bonds between the nitrogen and the oxygen atoms, okay, and make it decompose more readily. Okay, so now we have to calculate the value of X in this next question. Okay, right, first of all, let's do the dot cross diagram. Okay, hydrated magnesium nitrate was, we'll do the calculation bit in a minute. It says, just first of all, draw the dot cross diagram for the ions in magnesium hydroxide, show the outer electrons only. So magnesium, I'm just going to write down Mg is going to be 2+, and there's no electrons in the outer shell, so I won't draw anything there. Hydroxide ions, well, what are they like? Well, they're formed from water. Okay, so right, so you've got an oxygen, and you've got that's the bond to the hydrogen. Oxygen, of course, has got 6 of its own electrons. I've drawn 1 dot there, so we're going to draw 5 more. So 1, 2, 3, 4, 5. But this is OH minus, so it's got an extra electron. I'll do that in a different color. That's taken from somewhere else. So that is the OH minus ion there. Right. Now we've got to use the experimental data to calculate the value of X in the formula of magnesium nitrate, the hydrated version. Right, now what I like to do here is, if the approach is, we want to find out the MR of this thing, okay? Okay, if we can find out the MR of it, then we know how much the magnesium nitrate bit of it weighs, and so we can find out then how much the water weighs, divide through by X, and yeah, we should divide through by 18, which is the MR of water, and we find out what X is. So that's the approach we're going to take. Okay, so in an experiment, a sample of magnesium nitrate, that much mass, was dissolved in water and reacted with NaOH. Okay, you get a precipitate of magnesium hydroxide, which is dried and so forth, and the dried sample weighed that much. Okay, so we can work, we know the mass of that, we can find out the MR magnesium hydroxide. So the MR of magnesium hydroxide is going to be magnesium 24.3, oxygen 16, so that's going to be 58.3. So now we can work out the moles of magnesium nitrate, magnesium hydroxide, which is mass over MR. The mass is 0.174 grams, and the MR is 58.3. That gives us 2.984 times 10 to the minus 3 moles. Okay. Right. So from that, we can say that 1 mole of magnesium nitrate will give you 1 mole of magnesium hydroxide. So therefore, we can say the moles of MgNO3 to XH2O, that's the same as this number here, 2.94 times 10 to the minus 3. Okay, so we've got that. Right. Now we know the mass of that. It told us how much was, what was the mass of that much of the question there. You can see it is 0.765. So we know the mass and we know the moles. We can work out the MR. Okay, just write that down. So we've got moles is equal to mass over MR. So the MR is going to be equal to the mass divided by the moles. The mass of the hydrated magnesium nitrate was, tells us, was 0.765 grams. And the number of moles is that. And so that is equal to 256. Right. Now we've got to work out how many moles of water there. Well, we just work out the, so we've got our formula of magnesium nitrate here. Well, if you add up all that bit there, the MR of that bit is 148.3. So that means the waters have got to be this minus 148.3, which is equal to 5.98. Sorry, which is, sorry, is not equal to that. It's equal to 107.7. Now, what's the MR of one water molecule? Is 18. So how many times does 18 go into that? 107.7 divided by 18 gives us 6. X is equal to 6. Right, there are other ways of doing that. You can work out the moles of the water, the ratio, but that's the way I prefer to do it. Okay, and I think that's about halfway. So I'm going to end that video there and complete the second half of the paper in the next video.